Funding for this program was provided by the Annenberg CPB project.
In the early 1700s, the world of science turned its attention to the problem of electricity. There was a good reason for it. You see, many people who were scientists actually made their livings by giving lectures. Either they were itinerant lectures traveling from town to town, speaking to whoever would buy a ticket, or they were university professors. But either way, they had to attract an audience. Of course, today, university professors have guaranteed audiences, but that's because of the required course, which was a much later invention. In any case, they had to attract audiences, and for that purpose they wanted flashy, exciting demonstrations, and electricity was just perfect for that. A typical demonstration of the period was to get a street urchin, a little boy of 8 or 9 years old, and they would string him from the ceiling by silk threads, charge him up with an electrostatic charging machine, and have people draw sparks from his nose. I wanted to show you that demonstration, but all the street urchins were tied up. So I'll have to make do with these things instead. But before I show them to you, I'd like to explain to you a few simple principles of electricity.
Mechanical universe. Now this evening I'm going to be showing you some unusual things, but all of them utilize ordinary objects.
At first glance, the teaching scientist and the performing magician seem to have little in common.
Feel free to count them if you like.
And yet there's no doubt that each could learn a few good tricks from the other.
The two black kings.
Across the stages of history, whether one practiced science or sorcery, often depended on the observer's point of view.
A red ace. And if I'm not mistaken, I believe that's exactly halfway down in the pack. Now to find that card, I cut off about half the pack.
But no matter whether it was pure science or pure mischief, the ancient Greeks pursued it with a passion. The Greeks were quick in sport and science alike, and made a startling discovery early on about the nature of electricity.
Now it's a wand made of rosin, so if I were to rub it on the rabbit...
Certain materials act like a magic wand when rubbed against a rabbit's fur and attract small bits of matter.
Charge so that the paper flings as if by magic. And now take those bits of paper.
Eventually, scientists would be able to explain exactly how this phenomenon, electricity, really works. And unlike the professional magician, the early electricians were willing to share the secrets of their trade. For instance, one of the keys to electricity hasn't been a secret since Benjamin Franklin tried his hand in the field. He spread the word, and in simple English, this was it. Something called charge, the electric charge, is the cause of the electric force. That was brilliant as far as it went. But what was the connection between charge and force? In science as in magic, timing is everything. And in France, Charles Augustin Coulomb appeared with the answer. Coulomb's experiment, which revealed the relation between charge and force, could be verified by other scientists. And most convenient of all, it could be described in simple mathematical terms.
Coulomb's law states that the electric force is proportional to the product of the charges and inversely proportional to the square of the distance between the charges.
Furthermore, there are two kinds of charges, positive and negative. Electricity attracts when it acts between charges of different signs. But acting between charges that are the same, it repels. According to Coulomb's law,
the force two charges exert on a third is the vector sum of the forces each alone would exert. In fact, the forces from any number of positive charges and negative charges add together as vectors. So the total force is still calculated from Coulomb's law. Notice that positive charges are shown in red and negative charges are shown in blue.
Electric charge both exerts and experiences the electric force, and the electric force obeys Coulomb's law. It looks as simple as an 18th century electrical device, and on the surface, that's all there is to it. But electric charges don't exist in isolation. Instead, electricity resides in matter, the solids, liquids, and gases of the universe. And no matter the form it comes in, solid, liquid, or gas, matter itself is essentially electrical in nature. So to understand electricity, one must first come to terms with matter. On the other hand, to understand matter, one must first grasp the essentials of electricity. In fact, neither can be understood without the other. In his own study, Franklin began by thinking of electricity as a fluid, in some combination with matter. If there was too much fluid, he imagined matter to be positively charged with electric fluid. If there was too little fluid, he imagined the matter to be negatively charged with electricity. Therefore, in Franklin's mind, matter was in its proper state. That is, electrically neutral and balanced only when the right amount of electric fluid is present. Franklin was the first to see electricity in positive and negative terms. But rather than visualize two different kinds of charge, he saw either too much or too little of the same electric fluid. In the right hands, Franklin's single electric fluid became two kinds of electric charge.
Can then be split into four. Now they vanish one at a time into the cup, quite mysteriously.
Eventually, by accumulating knowledge piece by piece, scientists would put it all back together as a single structure, whose basic building blocks are atoms held together by positive and negative electric charge. At the core of every atom is a nucleus, which is made up of protons and neutrons. Protons contain its positive charge. The atom's neutrons have no charge, which means they're electrically neutral. The nucleus as a whole is surrounded by electrons, which have negative charge. And on the whole, each neutral atom has the same number of protons and electrons. The positive charge of each proton balances the negative charge of each electron, and they're bound together by the attractive electric force between them.
Now they vanish one at a time into the cup, quite mysteriously. When they reappear...
But this rather special balancing act, like any other act, is sometimes less than perfect. As a matter of fact, not all atoms are neutral. Some have too many electrons, or too few, in which case they're called ions. In fact, sodium ions with a net positive charge and chlorine ions with a negative charge are bound together by the electric force into crystals that make up ordinary table salt. But whether their atoms are ionized or not, solids, liquids, or gases, all matter in the universe is bound together by the force of electricity.
For instance, they could take this, a dull copper coin.
And of all the forms of matter, none exhibits the effects of electricity more clearly than metals.
Into solid gold. Gold. The stuff that dreams are made of.
Throughout the ages, scientists have dug deeply into the nature of metals. And in their quest, they've found that all metals have similar properties. For one thing, every metal is malleable and ductile, having the capability to change shape without breaking. Another age-old property is luster, the degree to which a shiny metal reflects light. For a long time, that was it. But in the 1700s, scientists found another property common to all metals. Today, it's called conductivity, the ability to conduct electricity. On an insulator, an electric charge stays where it is. But on a metal, it spreads out instantly. That is, the metal conducts electricity. On a deeper level, this is what happens. Each atom of a metal can be thought of as a positive ion with one or two loosely bound outer electrons. When two metallic atoms are very close together, the outermost electrons can pass easily from one to the next. As more atoms are added, electrons can range farther afield. Those mobile electrons are known as conduction electrons, and they give metals their special properties. In this way, all metals are electric conductors because every metal is like a giant molecule in which a number of electrons are shared equally by all the atoms. Picture it as a structure of positively charged ions, glued together by a fluid of mobile electrons. If a positive charge is brought near a metal, it attracts the mobile, negatively charged electrons toward itself, causing them to pile up at the nearest surface. The result is to leave net positive ions unbalanced by electrons at the far surface. The closer an electric charge gets to a metal, the more charge of the opposite sign builds up on the near surface, and more charge of the same sign is left on the rest of the surface.
And now an amazing little box I don't think you'll believe.
These properties are used in an instrument of science that may seem like magic. It's called a gold leaf electroscope.
Watch closely.
When an electric charge is brought near the metal disc, the gold leaf moves away from the rod.
Down. Float.
A positive charge near the top attracts negative charges, leaving positive charge at the other end of the metal rod, and the gold leaf is left with the same kind of charge. And of course, with the same kind of charge, the rod repels the gold leaf. When the wand is removed, the leaf falls back down, unless charge is transferred to the disc by physical contact.
Down. Float. Stay.
Physical contact leaves the rod and gold leaf with a net excess charge, and the leaf stays up. But it falls again at a touch of the hand.
Down.
The hand, which is itself a conductor, connects the post to the electroscope case. But where on earth did that extra charge go? The electroscope case is in contact with the Earth, which is a very big conductor in its own right. When contact is made, the electroscope, like any other conductor, shares its charge, releasing most of it into the larger body. Although in reality only negative electrons flow from one place to another, the effect is exactly as if positive charge flowed in the opposite direction. This is called grounding an electric conductor, or simply grounding. And for all practical purposes, when it happens, the conductor becomes electrically neutral. If that's the case, how does anything ever get charged in the first place? One way is friction, which is no surprise to anyone who's walked across a dry carpet and received a shock. But there are more effective ways to charge by friction.
That builds up a static charge so that the paper clings, as if by magic, to the rod.
In the 18th century, electricians devised machines that accumulated electric charge by rubbing a spinning insulator such as glass.
And now a little something I think you'll find quite electrifying. This is courtesy of my good friend, Mr. Van de Graaff. First, let's give it a little power.
In the 20th century, Robert Van de Graaff used the same principle. Charges stay put on the surface of an insulator to come up with a new twist. Down here, an insulating belt picks up electric charge. The conveyor belt carries the charge upward to the top of the machine, where the charge is transferred to the inside of the metal dome. Since metal is a conductor, the charge spreads out, and in the process builds up until it escapes by means of a spark and makes its way back to its old home, the ground. But Van de Graaff's machine had much more potential than a mere trick to spark the interest of a cabaret audience. In fact, its main feature, transferring electric charge by conveyor belt, is the principle behind one of the most important devices of the modern nuclear physics laboratory. This sturdy yellow chamber, by containing gas at high pressure, is designed precisely to prevent sparks from flying. Inside, with no sparks to discharge it, an enormous positive charge is built up by conveyor belt on the main terminal at the center. In the meantime, a negatively charged ion, in this case a carbon atom with an extra electron, is being prepared for an extraordinary journey. Started on its way by other negative charges, steered around a corner by one magnetic field, and kept at the center of the tube by another magnetic field. It soon feels the attractive force due to the positive charge on the main terminal. Accelerated by the electric force between the negative ion and the positive terminal, the ion streaks forward at high speed, until a collision with gas atoms strips some electrons, changing the ion from negative to positive. Accelerated once again by the electric force, the ion continues on to its destiny. In this case, a nuclear collision between carbon and a target of helium. This extraordinary machine is called a Tandem Van de Graaff Accelerator because it uses the enormous charge built up by the Van de Graaff generator, not once, but twice. Of course, using the positive charge twice is a trick of sorts, but it's still strictly science. not magic. And although Robert van de Graaff's conveyor belts are an excellent way to build up charge, Mother Nature's always had a few tricks of her own along those lines. Since the beginning of time, thunderstorms have involved huge buildups and releases of electric charge. Scientists believe the mechanism involves friction between ice particles in the clouds. But friction isn't the only way charge can be transferred.
But if I charge the stand,
this metal plate seems to be charged just by touching it.
notice an incredible reaction.
It's not magic, but there is a trick to it. If a positive charge is brought near a metal, negative charge will rush toward it, and positive charge is left behind on the other side. Then, if the metal is momentarily grounded, charge flows between the metal and the earth, leaving the metal negatively charged when contact is broken.
But if I charge the stand, you'll notice an incredible reaction.
That principle is called charging by induction, and it can seem like sheer magic to an audience that doesn't realize there are electric charges trapped inside the plastic sheet. That's why the metal plate seems to have been charged just by touching it. The trick is that touching the plate momentarily connects it to the ground, and that's what leaves it electrically charged.
This fascinating machine is not H.G. Wells' time machine. It is instead known as the Wimshurst Generator, one of several early ways of making electricity. Watch closely.
Invented in 1880 by James Wimshurst, an English engineer, this flashy machine features counter-rotating discs on which metal tabs are charged by induction, with contact being made and broken through metal brushes. As the wheels rotate, electric charge builds up until a miniature bolt of lightning relieves the mounting tension. One of the secrets of the Wimshurst machine's success is the device it uses to store up electric charge. It's the Leiden Jar, named after its birthplace at the University of Leiden. The principle behind the Leiden Jar is as simple as the device itself. In a Leiden jar, the inside and outside are metals, separated by the glass of the jar. If the inside is charged while the outside is grounded, the net result is equal amounts of opposite charge on both sides of the insulator. And those opposite charges are held firmly in place by the electric force between them. The Leiden jar was one of the best tricks of the 18th century electricians, who were often accomplished performers. Of course, the modern magician has a few tricks of his own, and the magician's tricks illustrate, above all, the greatest difference between magic and science. The magician's art is to confound the senses and create mystery. But the scientist's task is to expand the senses and solve mysteries.
A live hair. I'm sorry if this disappointed you. Maybe I can transform it into the kind of hair you were expecting.
Nevertheless, magicians do have one thing in common with the modern professor.
2 ears? Well, I'll have to get those fixed. Ladies and gentlemen, a live hair.
They both try to entertain, at least to the best of their abilities.
I wanted to show you that electricity can actually be useful. So when my young friend here told me that she wanted her hair teased, I thought maybe I would do it on this Van de Graaff machine. You know, this won't hurt a bit. There we go. Now watch what happens when I turn it on. You see that? Electricity can be absolutely hair-raising. She wanted to know how much this would cost, but I told her that by the time I was finished, there'd be no charge. Now, this thing is a different kind of electrostatic generating machine. It works by induction and by making and breaking contacts, but its basic purpose is it's a lightning machine. Its purpose is to throw sparks. Here, let me show you. You know, I thought they were going to give me an electric motor to run this thing, but when I read the fine print in my contract, it said that I had to crank it myself. Here, let me show you how it works. There you go. You see, it's a lightning machine. It's actually quite dangerous. If I were to grab the wrong thing at the wrong time, you could lose a professor. Or at the very least, you would learn a few words that aren't in the curriculum. The biggest machine of this kind ever made was made by a Dutch physicist named von Marum.
Long before the work of Wimshurst and Van de Graaff, back in the 1780s and 1790s, Martinus van Marum, in Holland, experimented with the largest electrostatic generating machine ever made. It had been built for van Marum by an English instrument maker named John Cuthbertson. Van Marum's giant machine used a bank of 100 Leiden jars. Its rotating discs were over 6 feet in diameter, and it could hurl a lightning bolt a distance of more than 2 feet.
It was a kind of electrostatic dinosaur, the end point of evolution of the 18th century electrostatic generating machine. And in a few years, it was extinct, because in Italy, Alessandro Volta had invented a far more elegant and useful device, one that would take electricity into a new era, the electric battery. We'll get to the electric battery in a short while, but first of all, I would like to tell you about another new idea, the idea of the electric field, and we'll do that next time.
Funding for this program was provided by the Annenberg CPB project.
To learn more about the Annenberg CPB channel series and workshops for teachers, how to take them for credit, how to buy them on video cassette, call 1-800-LEARNER and visit us at www.learner.org/channel. The Annenberg CPB channel.